Hello, today we are going to be talking about a very important theorem in the Hamilton-Jacobi formalism, which is known as Liouville's theorem. Okay, recall that we have been working with some generating functions S that are the solutions of the Hamilton-Jacobi equation. Okay, and we have been working with these functions of the form S equals a function of the qi, the upper pi, and the time, right? So we have been working with functions of three variables in this case. It's a function that it should be written in terms of these three variables. Remember that they are actually, well, 2n plus 1 variables, right? Because here I goes from 1 up to n, right? But the thing here is that we only have the q, the p, the upper p, and the t, right? So what the Liouville's theorem is going to help us to is to find a new function s, but it will only depend on the q's and the time. Okay, we will be able to take out the capital P's. And the key is going to be that, well, these P's are going to be considered as constants of motion that are in involution. Okay, so that is the first element of the theorem. It says here that if we have a function pi of the q's, the little p's, and the time, right, that are functionally independent constants of motion that are in involution, that means that the Poisson brackets between two p's, the pi and the pj, two arbitrary functions p, well, the Poisson brackets of this is equal to 0. That is what it means to be in involution. The thing here is that, well, they are constants of motion that are functionally independent. Okay? Okay, and it turns out that another requirement that we need is that, well, the momentas, pi, should be able to be written in terms of these three variables, qj, pj, and the time, right? Okay, so we can say that if we have those requirements, we can find a function of just the q's and the time such that, well, we can express that function as this equation that we have here, which is actually the definition of the total differential of S, right? Because remember that, well, if we have this function S that depends on the q's and the time, well, that means that ds is going to be, well, the partial of S with respect to qj, dqj, plus the partial of S with respect to time, dt, right? But remember that we have been saying that these generating functions, well, they represent some equations. That the first one is that pj is equal to the partial of S with respect to qj, right? So, as you can see, that is what we have here. I mean, pi times dqi, right? So this first part corresponds to, well, this first element of the equation. And then remember that, well, we have been saying that the generating function S has to satisfy the equation, the partial of S with respect to time equals to minus h. So that is exactly what we have here and here, right? So this is the total differential of S. Okay, perfect. So we are going to start to proving this theorem, and the first thing we are going to do is to calculate the total differential of the little p's. Remember that p, let's say pk, well, is a function of the qi, let's say qj, and then upper pj, and then the time, right? So if we calculate dpk, well, this is going to be the derivative of a pk with respect to qj, dqj, plus the partial of pk with respect to capital Pj, dpj, and plus the partial of pk with respect to time, dt. Okay, and now we are going to calculate, well, the total differential of the capital P's. Remember that this is little p, right? So here we said that these capital P's depend on the little q's, the little p's, and the time. So that means that, for example, pi is a function of qj, pj, and the time, meaning that the total differential dpi is the partial of pi with respect to qj dqj plus the partial of pi with respect to little pj dpj, and then plus the partial of pi with respect to time dt. Okay, perfect. So something that we can notice is that, well, this dpj can be expressed in terms of this definition that we have here, right? We can only switch the indices j maybe for the k to make it simpler, right? And we can solve, well, we can take this whole expression and into this element. So we will get that this is the partial of pi with respect to qj dqj plus the partial of pi with respect to pk, and then times, let's say, the derivative of pk with respect to qj dqj plus the partial of pk with respect to pj dpj plus the partial of pk with respect to time dt, and then plus the partial of capital Pi with respect to time dt, right? So notice something. We are calculating the total differential of the capital Pi, but here we have another total differential, well, yeah, the differential of Pj, right? So that means that, well, we can do something with that. First of all, notice that, well, I'm going to rewrite this equation in a different way. Let me say that this is the partial of capital PA with respect to qj dqj, and then plus the partial of pi, and let me factor this qj, right? It will be plus the partial of capital Pi with respect to little pk, the partial of little pk with respect to qj, and then all this multiplies dqj, right? I'm taking this qj and this qj as common factors. And then we will have that plus the partial of capital Pi with respect to pk, the derivative of pk with respect to pj, and then times dpj, okay? And then we will have plus the partial of pi with respect to pk times the partial of pk with respect to time, and then we will have here, let me move this to make some space. Here it sums with the partial of capital PA with respect to time, then we factor dt, okay? And recall that this is equal to dpi, right? Perfect. So what can we say about this? I mean, look that we have here that, well, we have this element and this element, right? So let's examine what happens with this. We are going to write a dpi with respect to pk, dpk with respect to pj times dpj. Okay, perfect. So the thing here is that notice that we are kind of like using some kind of chain rule here with these two elements, because this can be seen as, well, the derivative of pi with respect to pj, right? Okay, yeah, just by using the chain rule. So the thing here is that this quantity can be seen as the derivative of capital Pi with respect to capital Pj dpi. But you should know that, well, we are taking a very intuitive derivative, right? It's like having maybe the derivative of x with respect to x, which is 1, of course, because x is equal to x. But this means that, well, this derivative is going to be just a Kronecker delta ij, right? Because it will be 1 when I is equal to j. That means that we are taking the derivative of, for example, p3 with respect to p3. So that is equal to 1, right? So only when I is equal to j, we'll have something different from 0. And when I is different from j, we will get 0 all the time. So that means that this is equal to Kronecker delta ij times dpi, which is of course dpj. So this means like all this stuff that I have here is equal to dpi, right? So the thing here is that with these all results, we can get that dpi is equal to, well, this dpi that we just found, dpi, and then plus something times dqj plus something times dt, right? So with this very weird equation, maybe, we can say that the things that are multiplying the dqj and the dt, well, they need to be equal to 0 to hold the equation, right? Because this needs to be equal to this, of course. But if we sum this, the equality is broken, right? So the thing here is that this element and this element should be 0. That is the important thing. Okay? So that means that, well, this quantity is equal to 0 and this quantity is equal to 0, right? So I'm going to write these results in this position of the page. That is, the partial of pi with respect to qj is equal to negative the partial of pi with respect to little pk, and the partial of little pk with respect to qj. This is the first result. And the other one was the derivative of capital Pi with respect to time is equal to negative the partial of capital Pi with respect to little pk, the derivative of little pk with respect to time. Okay, so here are two important results that we are going to use later. Okay, that remember that they come from here and here. Okay, perfect. Okay. So now we are going to make use of one of the hypotheses that we mentioned at the beginning of the lesson when we wrote the Liouville's theorem. That is that, well, these upper p's are in involution. Recall that they are constants of motion. And we are going to calculate the Poisson brackets between pi and pj, and this needs to be equal to 0, right? They are in involution. So what are we going to get if we do this? Well, this is going to be first, well, the derivative of pi with respect to, let's say, qk times the derivative of pj with respect to pk minus the derivative of pi with respect to pk, the derivative of pj with respect to qk. Okay, but recall that we have just found what is actually the derivative of capital P with respect to Q, right? So we can use this formula into this equation that we found to get another result. So this is going to be, let's say maybe that this is minus the derivative of pi with respect to little pm, the derivative of little pm with respect to qk, right? I'm using this formula that I have here, just with different indices, right? And times the derivative of pj with respect to pk. And if we make the same thing with this minus and this minus, we are going to get a plus, right? So this will be the derivative of pj with respect to, let's say, pm, and the derivative of pm with respect to qk, and then the derivative of pi with respect to pk, which corresponds to this element. Okay, perfect. And here, for convenience, we are going to switch the indices. I mean that this m will become a k, this also, and this case will become an m. Okay, this is just to be able to have two common factors. You can see here that we have the derivative of pi with respect to pm, the derivative of pi with respect to pm, and the derivative of pj with respect to pk here and here, right? So we are going to take that as a common factor to get that, let's say, the derivative of pi with respect to pm times the derivative of pj with respect to pk is going to multiply this thing, the derivative of little pk with respect to qm, minus the derivative of little pm with respect to qk. Perfect. Recall that this needs to be equal to 0, and looking at these capital P's depend in the little p's, right? This little pm and this little pk. This is not going to be equal to 0. Actually, this is different from 0, right? So here we can say that, well, the derivative of little pk with respect to qm is equal to the derivative of little pm with respect to qk. Perfect. This is another important result that we are going to use. Okay. Another hypothesis that we are going to use now is that, well, these upper p's, well, they are constants of motion, right? So if they are constants of motion, that means that pi dot is equal to 0. Okay, so we need to calculate the derivative with respect to time of pi, which is a function of qj, little pj, and the time, right? So how are we going to use this? Well, let's say that, and this is equal to 0, right? So we will have that 0 is going to be equal to, well, the partial of pi with respect to qj times, well, we will have here the derivative of qj with respect to time, right? But that is qj dot. Perfect. And then plus the derivative of capital Pi with respect to little pj, and then, well, pj dot. And then plus the partial of pi with respect to time. Okay, perfect. And here we are going to make use of the Hamilton equations that are very well known. You know that qi dot is equal to the partial of h with respect to pi, and that pi dot is equal to the partial negative, the partial of h with respect to qi. Okay, so if we do this, we are going to get that this is the partial of pi with respect to qj, the partial of h with respect to little pj, plus the partial of capital Pi with respect to pj, and then this will be a minus, right? The partial of h with respect to qj, plus the partial of pi with respect to time. You should notice something here. We have this element, and the derivative of pi with respect to qj, and the derivative of pi with respect to time. Okay? You should remember that here we found some equations to express those elements. So we are going to use these two equations. Yeah, let me copy them to see what are we going to get in that equation that we found. Okay, so if we substitute, we are going to get that 0 is equal to, let's say, minus the partial of pi with respect to pk, the derivative of pk with respect to qj, and the partial of h with respect to pj. And then, well, this element is going to stay the same, so it will be minus the partial of capital Pi with respect to little pj, the partial of h with respect to qj, and here, well, we are going to substitute this to get minus, it will be the partial of pa with respect to pk, the partial of pk with respect to time. Okay, we are going to do something similar to what we did before. This j is going to be switched for a k, right? To be able to have a common factor, the derivative of pi with respect to pk, right? So we can say that this is equal to negative the partial of capital Pa with respect to pk, that is going to multiply the derivative of little pk with respect to qj, the derivative of the Hamiltonian with respect to pj, plus the partial of h with respect to qk, plus the partial of little pk with respect to time equals to 0. Remember that this quantity in general is not 0 because pi depends explicitly on pk, right? So this means that the thing that is between the parentheses is going to be equal to 0. So this takes us to have that the derivative of pk with respect to qj, the derivative of h with respect to pj, and these are all little p's, right? And then plus the derivative of h with respect to qk plus the derivative of pk with respect to time is equal to 0. Okay, so what can we say about this? Well, we are going to solve this equation for this element to get that the derivative of pk with respect to time is equal to negative the derivative of pk. Let's say first the derivative of the Hamiltonian with respect to pj, and then the derivative of pk with respect to qj, and then minus the derivative of h with respect to qk. Okay, perfect. And here is where we are going to use the other equation that we found, this one over here, the one that, well, it switches the indices, right, of the derivatives. I mean, we have the k here in the numerator, and then we take down the index to the q right here, and then the m, we take it to the m, right? So we can just switch the order of the indices. So that means that we can take this expression to get pj and then qk here. Okay, perfect. So with this, what can we say? Notice that this element can be seen as the derivative with respect to qk of h. Yeah, if h is only a function of pj, which is a function of qi, let's say, for example. The thing here is that we know that h is also a function of qj, right? And maybe the time. But you should notice with this that if we take this derivative, well, we are going to get exactly what we have here. I mean, taking the derivative of the Hamiltonian with respect to qk is going to be taking the derivative of h with respect to first this pj, and then the derivative of p with respect to the q, right? The derivative of pj with respect to the qk. And then looking that the Hamiltonian also depends on the little q, we are going to take here the derivative of the Hamiltonian with respect to qk. So the thing here is that that is exactly what we have here. So we can say that the derivative of little pk with respect to time is equal to the, well, minus the derivative of the Hamiltonian with respect to qk. Where here, the Hamiltonian, well, it depends on qj, pj that depends also in qi, the capital Pi and the time, and this Hamiltonian also depends on the time, right? So the thing here is that, well, we have this expression over here. So what does this mean? I mean, this is already telling us that the differential that we defined here at the beginning, this total differential here, well, it is an exact differential, right? But why is this? Well, we are taking the derivative with respect to time of the pk, which is being equal to minus the derivative with respect to qk of h. The thing here is that we know that every pi is defined as the partial derivative of s with respect to qi, right? And then we know that the partial of s with respect to time is equal to minus h. So we can say from here, and let me switch this index for a k to watch it more clear. We can say that the derivative with respect to time of pk, which is the derivative of s with respect to q, is equal to minus the derivative with respect to qk of h, but h is minus the derivative of s with respect to time. So we can say from this that the second derivative of s with respect to qk with respect to time is equal to the second derivative of s with respect to time with respect to qk. So we can say that the order of the derivatives doesn't matter. I mean, you can take first the derivative with respect to q and then the derivative with respect to t. But you should know from differential equations that, well, this is a requirement for the total differential to be exact. I mean, with this we can guarantee that the differential ds defined in this way that we have here is exact. Okay? Perfect. So this means that this function s that depends only on the q's and the time exists, and well, looking that it satisfies the equations of the generating function that we use to solve the Hamilton-Jacobi equation. Well, it turns out that that means that this s is a solution of the Hamilton-Jacobi equation. I understand that maybe this topic could be a little bit confusing, but we are going to be making examples of this to find, well, that differential, and then this differential is going to tell us what is that function s that is the solution for the Hamilton-Jacobi equation for some examples. So, I mean, we are going to use the Liouville's theorem to construct this differential s by using p dqi minus h dt, and with this, by constructing this differential s, we are going to be able to see what is the structure of s, and then that is going to be our solution for the Hamilton-Jacobi equation. But that will be seen in further examples in other lessons. Okay, so for now I think I'm going to finish the lesson right now. I hope you enjoyed the video.